So, previously we learned about s orbitals, p orbitals. Where are these electrons located at in these orbitals? And what do we care about? The inside orbitals, inside electrons or outside electrons? We care about outside electrons, right? And those are called valence electrons. So we have one atom going to come together with another atom. What's going to touch first?
Valence, the
Valence,
valence electrons.
valence electrons, right? So, and then when they come together in a certain way, maybe they're going to do something. Maybe they don't do something. And one of the things they can do, they could form something called a bond, right? So when atoms are by themselves, okay, they're atoms. But when they come together, they form molecules or compounds. And what holds them together to stay as a molecule or stay as a compound is something called a bond, a connection between these atoms. Why is there a connection? These atoms only have protons, electrons, and neutrons. Why is there what's connecting them? And what's on the outside of the atom is the electron. And the electrons are going to be doing something. So there's some theory about bonding. Right? In this chapter, we're going to talk about, okay, like water. Why is water H2O? Why is water H2O? Why isn't it H3O or H4O or H5O, right? Why does it come together like this? Why not like this or this, right? And then we're going to discuss why this doesn't happen in this chapter, once we understand the theories about bonding. Right? Well, someone mentions that oxygen has a charge of 2. Then the next question is, why does oxygen have a charge of -2? Right? So we give it a charge of -2 to try to explain what's going on. And in this chapter, we're going to
Isn't it because H has a charge of +1 and there's 2 H molecules?
So
It's
that's
to
what we
balance it out.
learned. Yep, that's what we learned previously. Now the next question is, why does H have a +1 charge? Okay. So before we just told you this is +1, this is -2, this is +2. But now we're going to talk about why that is so. All right, and then once we get once we could predict what the formula is, then the next step is to figure out what is the shape of the molecule. Is it a triangle shape? Is it a linear shape? Is it a square shape? Next thing is to figure out the shape, and that's what we're going to be talking about in this chapter. So now there's something called a Lewis structure. Oops. So we're going to talk about something called Lewis bonding theory. So it's a simple bonding theory. It's not the most up to date, but it's just a nice simple theory that it's going to help us introduce us to bonding. And before we could get into that, we got to talk about something called Lewis structure. And basically it's a electron dot structure. We're going to talk about what does that mean. So why do atoms bond? When one atom comes together with another atom, aren't these electrons going to repel each other when they come closer together? So, electrons are going to repel each other. Too close, maybe the nucleus of this atom and the nucleus of this atom are going to repel each other, right? But so you got a lot of repulsion, but you got some attraction. Maybe this proton is going to start attracting that electron. So you got some attraction, you got some repulsion going on, right? And then one thing we notice is something called the octet rule, and we're going to talk about this a little bit later, but for some reason, atoms like to have 8 valence electrons. So things want to have 8 valence electrons. Okay. So this is like a little introduction. So when we put 2 atoms together, they're going to want to repel, but they're also going to want to attract. And then we got both repulsion and attraction forces. And then figure out, why do atoms come together to form bonds? So one thing what we notice is noble gases. So what element on the periodic table are noble gases? Column 1, column 2. Which column are noble gases?
8A. Wait,
8.
yeah, 8.
So what do we know about column 8? How many valence electrons in column 8?
8.
8. But when we do chemistry of noble gases, we'll get the chemical, and then we'll try to do a chemical reaction. And you know what happens? No reaction. If I heat it up, I mix it with 100 different other elements, nothing happens. Mix it up, stir it up, heat it up, whatever I do, it doesn't want to form compounds with anything. Why not? That means noble gases are stable or inert. They're happy by themselves. They don't need another atom. So they're very stable and they're happy. Right? So that's what we learn about noble gases. And then, so based on that, let's look at this. We talked about ionization. Look at this electron configuration for noble gases. You see some type of pattern there? These all have column 8, so they all have 8 valence electrons. Helium doesn't have 8 because it's too small, but helium has 2. So all these have 8 valence electrons, and they're very stable. So we'll learn about valence electrons. So one thing what we think about, okay, maybe there's something special about this 8. Oops. If I could get to 8 valence electrons, then I'm going to be happy. It's like when you eat your dinner, you're nice and full. Are you happy? Yes. Can I eat more food? Oh, I could, but I'm happy. I'm not going to eat anymore. So that's like you have a full stomach. So think about 8 electrons as like a full stomach. If I don't have a full stomach, oh, I need to eat a little bit more. Or if I do have a full stomach, I don't want any more. So think about you're happy at 8. Oops. And then what we notice is there's different types of bonds out there. There's something called ionic, covalent, metallic. So we're going to be focusing on mainly ionic and covalent so far. And there's a little bit, maybe a little bit about metallic, but these are the main focus ones to focus on. So what do we care about electrons? We care about valence electrons, right? And so let's look at this boron. And what's the electron configuration for boron? He, 2s2, 2p1. This has how many valence electrons?
3.
Anyone could tell me?
3.
3 valence electron. Has a total of 5 electrons, but valence electrons 3. So how are we going to draw this out? We're going to write down the symbol boron, B for boron. And then what do we say? How many valence electrons? 1, 2, 3. So each dot represents an electron. Sometimes you might see the boron as like this, 3 separate electrons. But here they draw it as 2 electrons on one side. Why is that? Because these 2 electrons here are in the same orbital, and those represent those 2 electrons there. And this electron represents that electron right there. So this is called the Lewis structure. And who came up with this idea? This guy named Lewis, right? And again, you guys, probably don't think much about chemistry, but chemistry is really, really big in California. Has a strong history. So this guy Lewis is from California. I think he was either Caltech or UC Berkeley. I can't remember. So he came up with this system. Okay, write the symbol and then write the valence electrons as dots. So we could write down the electron configuration like this, right? That's a lot of work. Now, because what do we care about? Valence electrons. So let's just write the Lewis symbol. Right? Sodium is located on what column on the periodic table? Column 1, 1 dot. Magnesium, column 2, 2 dots. Aluminum, column 3, 3 dots. Argon, column 8, 8 dots. Chlorine, column 7. Right? Look at this. Oops. And we said this is a noble gas, right? Argon has 8. So for some reason, argon is very, very stable. And we just say, okay, let's make an assumption. And we have 8 valence electrons, you are stable. Electrons don't want to come in, and electrons don't want to come out. So you're very, very stable. Look at chlorine, has how many valence electrons?
So
7. How could chlorine become like argon?
needs to gain
It needs to gain how many?
1.
1. So that's where we get this idea of chlorine is minus 1. Because chlorine just needs one more electron to become like argon. So let's check if that's true or not. Let's do some experiments. So we got sodium, our Lewis structure, chlorine, our Lewis structure. So what happens is, this is an example of something called ionic bond. What does ions mean? Anyone remember? Ions mean charge.
Charge.
Right? So this is a bond based on charge. So let's see what happens. I get sodium, chlorine, all right? Sodium has 1 valence electron, chlorine has 7. The chlorine goes, oh my gosh, I just need one more electron to become like a noble gas. So the chlorine really, really wants 1 electron. But what is sodium? Electron configuration for sodium. I can't, oops. Can sodium gain 7 more electrons to become like a noble gas? Could, but that's just so many, right? What can sodium do to become like a noble gas electron configuration? What do you think the easiest way for that sodium to become like a noble gas in terms of electrons?
Pass it on to another element.
It could lose 1 electron because look at this. When the sodium loses an electron, which loses is going to lose that electron right there, right? And what's left over? I'm going to look like a noble gas. So sodium wants to lose an electron. Chlorine wants to gain an electron. Is that a good combination for them to team up? So what happens is this sodium is going to give away the electrons, chlorine is going to gain it, and then once the sodium gives it away, what do we have? A plus charge on sodium. When chlorine gets that electron, what are we going to get? A minus charge. What happens when we have a positive, a plus charge and minus charge? What's going to happen to it? Are they going to repel
Repel.
or come together?
Come together. Because
Right?
they're opposite.
That's where we get this. Yep. Plus and minus. So this is where we get this idea. You ever heard the saying, opposites attract? You ever heard that? Opposites attract?
Yeah. We all heard that relationship advice.
This is where we get it from. Positive and negative charges, they attract. They're opposites and they attract. They come together. When you get a plus and minus come together, you get a bond, connection. And what type of connection? Based on charge, that's called a ionic bond. Okay. So, oh, do I ever get something like, every time we put sodium and chlorine together, we get this. One sodium, 1 chlorine. Do we get 3 sodiums and 1 chlorine? No. Every time we get this one, 1 to 1. Why is that? And it's because chlorine only needs 1 more electron to get to 8. Sodium just needs to give away 1 electron to get to 8. So this one loses 1, this one gains 1. So it's a perfect combination of sodium chloride. It's not going to be sodium trichloride or trisodium and three of this and 1 of that. No. Even though we try to make something like this, it doesn't happen. And that tells us, this is always 1-to-1 relationship between sodium and chloride because chlorine just needs 1 electron. Sodium wants to give away 1 electron. And that's where we get this idea, chlorine is -1, sodium is +1. So let's do another example. Here's another one, calcium. Calcium has, this is a Lewis structure, column 2 on the periodic table, has 2 electrons. Fluorine has 7. How could these two combine. So calcium wants to get to a noble gas configuration, but it needs 6 more. That's too much. So what's it going to do? It's going to lose these 2 electrons. And fluorine needs 1 more electron. So what's going to happen? One of these electrons is going to go to this fluorine, so that fluorine could get to 8. But when we do chemical reactions, can we do chemical reactions with 1 atom here and 1 atom over here? No, we're going to do Avogadro number of atoms here, Avogadro number of atoms there. Okay. So when you do that, Avogadro number of atoms, is there more than 1 atom lying around? Yes. So look at this, fluorine. Okay. So suppose there's 1 electron is going to go to this fluorine, and then 1 electron is going to go to that fluorine. Right? Because there's going to be more than 1 fluorine, right? We're calculating Avogadro number, right? Okay. Then, what do we have here? When we cut calcium, oops. So I get powder of calcium, powder, a bunch of fluorine together. I mix them together. What do I form? CaF2. I don't form CaF10 or CaF20. I always form CaF2. Why? Because calcium is going to lose 2 electrons, and fluorine is going to gain 1 electron each. And this combination gives us 8 valence electrons for fluorine, and then calcium is lose 2 electrons to give us a noble gas configuration. So where do we get this +2 charge and minus charge for fluorine? It's because fluorine wants to gain 1 more electron. Why? Because it wants to look like a noble gas in terms of 8 valence electrons. Calcium, same thing. It wants to, instead of gain electrons, it's going to have to lose electrons. How many electrons does it have to lose to become like a noble gas? It has to lose 2. So when you put calcium and fluorine together, calcium wants to lose 2 electrons, fluorine is going to want to gain 1 each. And every time we mix them together, we get this one, CaF2. We don't get CaF10 or CaF20 or CaF, always get this one. And what type of model or what type of theory can we predict CaF2? Because calcium wants to lose 2 electrons, fluorine wants to gain 1 electron. Combined together, we want to have a 0 charge total. So that's kind of our theory of how ionic bonds work. These atoms want to get to 8 valence electrons. How are they going to get to 8? One atom is going to donate, another leave it. Once he donates it, we're going to have a plus charge. Whoever receives it's going to have a minus charge. And what happens when we have plus and minus? They come together to form a ionic bond. And what's the total charge of this compound? 0 charge. And that helps us what this formula is, calcium F2. Right?
So
we don't form calcium F5. Yes?
So if how to say this? So for H2O, right? The reason why it's H2 and O is because the H is giving 2 of its well, since it's 2 hydrogens, right? +1 charges and all that. Both of those already have given its plus charges to its O, to the oxygen and all that, and it makes it full. That's why so you said that why is it not like 5H5O and all that? It's because it's already full. Is that what you're saying, right?
Yep.
It's full of valence electrons.
Yep. So look at this.
It's already a noble gas.
Yep. You're a little bit ahead of us, but yes. So look at this oxygen here. How many valence electrons does oxygen have? 6. It's on column 6. So how many more electrons does oxygen need to get to 8? 2 more. Where can it get those 2 electrons from? 1 from this hydrogen, 1 from that hydrogen. And then oxygen is going to be happy at 8. So, but we're not there yet. So H2O is not an ionic bond, it's a different type of bond. And we're going to get to that later. So
can I say one more thing? So if I were to add one more H to it,
Huh?
what will happen to that H? Will it just be out of the way? Like be
One
leftovers,
more
kind of
age.
like leftovers.
You can think about leftovers, but in real life, we're not talking about one atom or two atoms. We're talking about Avogadro number. So there's millions and millions of these. So they're all going to find a partner. There's not going to be any leftover. But we're
So
a
it
little
has
bit
to
ahead of
go
our.
somewhere then.
Yeah, so we're not there yet. This is ionic bond. H2O is something called a covalent bond. We're going to talk about that in 30 minutes from now. So we're not there yet. But great question. So we have something called sodium chloride because right, it's based on charge, right? And then when we look at it under a special type of microscope, a certain type of instrument, what we see is it's like a crystal. For salts, they bind like a crystal. What does that mean? If I have a sodium here, it's going to be it's going to combine. Let's see, it's going to combine with chlorine over here. This chlorine is going to have another sodium over here, another chlorine. So it's like a big array, a big mesh. Sodium chloride, sodium chloride, sodium chloride. So in this crystal, we have like a million sodium and a million chlorides. Are we going to say sodium 100, chlorine chlorine 100? No. We look at the simplest repeating pattern. What's the simplest repeating pattern? One sodium and one chloride. So that we call this thing sodium chloride. We're not going to say sodium 1 million, chloride 1 million. No, 1 to 1. Because this is based on charge, because I have a sodium here, it's going to connect to this minus charge. This sodium is going to connect to that minus charge there. This chlorine here is going to connect to this positive charge there. So this is all based on charge. Based on charge, you're going to get this like plus, minus, plus, minus, plus, minus continuously. But the simplest repeating pattern is one sodium, one chloride. Why do you think they draw the sodium smaller than the chloride? You guys remember? Because when I add an electron to the chlorine, where is that electron going to go, to the inside of the atom or the outside of the atom when I add an electron?
Outside, because it's a valence electron, right?
Yep. If I add it to the outside, is the atom getting bigger or smaller?
Bigger.
Yep, so it got bigger. Sodium, I'm removing an electron. Am I removing an inside electron or outside electron?
Outside.
Outside, right? So I remove an electron, what's going to happen to the size of the atom? It's going to get smaller. So plus charges, atoms get smaller. Minus charges, atom gets bigger. So they drew this kind of to scale. And then this is your sodium chloride. All the ions are in place, plus, minus, plus, minus. These charges don't move. They're locked in place because it's a solid. If I get this sodium chloride and I heat it up, then these plus, minus charges are all going to be moving around. When I heat it up, I mean like melting it. So this is more like a liquid, and these ions can move. So if you did that conductivity experiment, this one, a solid, does not conduct electricity, but this as a liquid, or if it gets dissolved, this one conducts electricity. And we call these things like salts. Sodium chloride, we call it salt. But because this thing conducts electricity, what do we call that? We call that electrolytes. Anything that conducts electricity is an electrolyte. So what do you guys buy at the store that contains electrolytes? Gatorade, right? That's why they say, oh, Gatorade contains electrolytes. Or you want to buy a Gatorade that says, "Oh, Gatorade, we have salt in our Gatorade." So electrolytes. And electrolytes, we need that for our body. We need salt in our body because when we sweat, salt comes out. So we need to replace the salt that we lost. So and we need a little bit of salt. And here is just pointing what we talked about before. Lithium. This is the radius of lithium, 0.15 nanometer. When I take an electron away, what happens? The ion gets smaller. So look at all these, and what happens when I have a plus charge? They all get smaller. Because I'm removing an electron. If I remove an electron, my atom's getting smaller. Because I'm removing an outside electron. All right. Then we have this one over here. Oops. Fluorine. And what happens to fluorine? Fluorine gets, if you add an electron, this is the radius of fluorine. When you add an electron, the atom, this ion is going to get bigger, right? When we add an electron, we're going to add it to the outside of the atom, and this other atom's going to get bigger. So when we're removing an electron, gets smaller, add an electron, gets bigger. Kind of makes sense. So we have these certain type of equipment that we could actually measure the radius of an atom. And maybe around chapter 10 or 11, towards the last week of class, we're going to talk about how that is done. So that's an example here is sodium here, sodium plus here. How do I get to sodium plus? I have to remove an outside electron, 3s1. Yeah, 3s1's not there anymore, right? So this one's going to get lost. When that one gets lost, it becomes smaller. On the bottom case, chlorine. This is the electron configuration. Chlorine minus, I'm gaining one more electron, so the atom is going to get a little bit bigger whenever I gain an electron. So this is a topic we talked about before, right? Electron configuration. Look at these electron configurations. You guys see something similar to these?
We all have 6 as a valence electron.
Anything else?
Oh, the first 2 sublevels literally are the same.
Identical. Right? Oops. Lost my pen. Okay. How can they all have the same number of electrons? Because look at this. Right? The identity of the atom doesn't depend on the electron. The identity of the atom depends on the number of protons, right? If I just add electrons or subtract electrons, I could have different number of different electron configuration for each atom. So here, sodium plus, noble gas configuration. Magnesium 2 plus, noble gas configuration. Aluminum 3 plus, noble gas configuration. Fluorine minus, noble gas configuration, right? So all these atoms are on level 2, same configuration. So which atom is so here's a question, which ion is the smaller? Out of all these, which is the smaller one? Or are they the same size?
If they're all identical, wouldn't they all be the same?
Okay, that's one answer. They might be all the same.
According to this,
Think
they're the
about,
same, but not necessarily.
Yeah.
okay. I think you guys are using more like a qualitative judgment. Now you got to think of more like quantitative measurement to answer your question. Don't trust your eyes. You got to trust your logic.
Is it because of the number of protons it has?
Okay, what about that? You're on the right track. How many protons does sodium have? I think it's number 11. Magnesium. I can't remember that. Magnesium has. Look at my periodic table here. Magnesium has 12. This one here has 12. Aluminum has 13. I don't memorize these things. You just have to look at it, know how to read the table. This one has 9. Oh, shoot. This one has 9. All right, now let's see how many electrons we have. 8, 8, 8, 8. So which one of these is going to pull the electrons really tight to the center?
Fluorine. No, sorry, F. Was it fluorine? Yeah, fluorine.
Which one's going to hold the electrons really tightly? The one that has 13 protons or the one that has 9 protons? Which one's going to hold the electrons really tight?
9 protons.
No. If I have more plus charges, the more plus charges, are they going to attract the electrons more or less?
More.
So which one's going to hold the electrons tightly at the
13.
center? This one here, right? If it holds it more tightly, am I smaller or bigger?
Smaller.
Smaller. See that logic flow? Many steps, right? And at the beginning, you guys look at this, oh, shouldn't it be the same size? That's common, right? Oh, same number of electrons. And then you got to step back, oops, and think, okay, same number of electrons or protons. What did we just say? Opposites attract. So we got, now we figure, oh, this one has the most protons. That means they're going to attract these electrons more tighter. And they attract them more closer, they're going to be a smaller one. The answer is going to be aluminum. A simple question, but you have to think multiple steps. Right? Which element forms an ion that is larger than its atom? So why don't you guys work on this for 1 minute, see what you guys get. Have an idea? Vote A, B, C, or D. Nobody has an answer? What do we got here? No answers? No guesses?
C.
See? Okay.
Yeah. See.
See? Okay. So, okay. Oops. Which element forms an ion? Okay. They're all going to form ions. So if this one forms an ion, what type of ion is going to form? Lithium minus or lithium plus?
Plus.
Lithium plus.
Plus 1.
Where is lithium on the periodic table? Column number 1.
3.
And lithium wants to lose an electron to become like a noble gas. Calcium, is that plus or minus when it becomes an ion?
Plus.
Plus. Oh, I'm going to say plus 2, right? But it's chromium.
Plus.
Chromium is a metal. What do we know about metals? Metals form plus charges. Fluorine is going to be a plus or minus charge.
Minus.
Why is fluorine a minus charge?
Because it's close to the noble gas.
Yep, and he needs one more electron to become like a noble gas. So it's going to become minus. It's going to grab an electron from somewhere. So which one of these is bigger than its original atom? If I get a plus charge, am I getting bigger or smaller if I'm removing an electron? Removing an electron, am I getting bigger or smaller?
Smaller.
If I'm adding an electron, am I getting bigger or smaller?
Bigger.
Right? Okay. So there's only one thing on this, on A, B, C, or D, that's getting larger. That's D. Simple question, but you have to think. It's a lot of steps. And everything what you learned before, we just gotta apply it now. But the thing is, you learn so many different things, it's hard to understand what do you need to apply, right? All right, let's look at this one. Magnesium, I get magnesium and I get chlorine, I put it together, what do I make? Magnesium has 2 valence electrons, chlorine has 7. So what's going to happen? One of these electrons is going to go to one of these chlorines, another electron is going to go to another chlorine. And when I have that, I'm going to have one of this and 2 chlorines. And what do I make? Right there. MgCl2. Every time I mix this and chlorine together, I always get MgCl2. I don't get MgCl5. No, I always get 2. Doesn't matter how I mix it. Heat it up, stir it up, shake it, heat it for a year, heat it for a month. Always get only 2, MgCl2. And then why is that? Why in nature are we only? Why does nature only let us make this? Because we come up with something called the octet rule. This chlorine wants to get to 8 electrons. This magnesium wants to get to 8. How could they both get to 8? Magnesium has to donate 2 electrons, and calcium has to gain 1 electron. When that happens, I'm going to get a +2 charge on magnesium, minus charges on the calcium, on the chlorines, and then we have a plus and minus charge. What's going to happen? They're going to come together. Give us magnesium chloride. Why don't we just say magnesium dichloride, right? Shouldn't that be the name? 2 chlorines, so magnesium dichloride. You know why we don't do that? We just call it magnesium chloride. Because every time I add magnesium plus chlorine, there's only one combination I can make. And that one combination is MgCl2. So since there's only one type of magnesium chloride, we just call it magnesium chloride instead of magnesium dichloride. Now, if it's possible to make something like this, yes, then we have this, we can't call this one magnesium chloride and call this one magnesium chloride. We got to give it magnesium dichloride or magnesium trichloride. But in real life, things like this don't exist, and we know that. So we know that when we combine magnesium chlorine together, there's only one possible combination, and that's 2 chlorines. So we just give it a simple name, magnesium chloride. Even though in theory, it should be called magnesium dichloride, but in real life, there's only one type of magnesium chloride. So we just call it magnesium chloride, if that makes sense to you guys.
So the reason why we have to balance an equation is because of the whole valence electrons and all that, right?
No,
No?
balancing equation is matching up the number of atoms, not the electrons. You match up the number of electrons, that's called a redox reaction, oxidation reduction. So that's a little bit different. So there's balance a chemical equation, number of atoms, and then if electrons are moving around, then that's called the redox, oxidation reduction. Yes, and then you have to balance those electrons. But we have to figure out where they're moving, if they're moving. So now that's called the ionic bond. The electron is completely removed from one atom and it goes to another atom. They're not sharing the electrons, it's completely removed. When it's completely removed or completely taken, you get a plus charge and a minus charge. And what happens when you have a plus and minus? They're attracted. Then there's something called the covalent bond. So we're done with ionic bonds. Ionic bonds are transfer of electrons. And when you transfer an electron, you lose the electron or you gain the electron, you become a plus or minus charge. And when you have a plus or minus charge, that plus and minus charge come together. So now let's look at this one. Hydrogen and this hydrogen. This is the Lewis structure for each one. One dot and one dot. Can one hydrogen remove an electron from another hydrogen? So think about this is one twin brother. This is another twin brother, and these dots are this toy. Can one twin brother rip the toy away from the other twin brother? You know why? Because these are identical twins. Is one twin stronger than the other twin? No, they're identical, perfect identical. So they're not strong enough. One twin brother is not strong enough to remove the electron. So what do you know about brothers or sisters or siblings? Instead of taking it away, what do they have to do? They're going to have to share the toy. But here, instead of sharing the toy, they're going to share electrons. So what happens is, what's a noble gas? Helium, right? How many electrons does helium have? 2. So this hydrogen is too small. It can't get to 8 valence electrons. So hydrogen wants to become like helium, to get to 2. How could this hydrogen get to 2? It has to take away that electron, right? But it's not strong enough. So instead of taking it away, what they're going to do, they're going to share the 2 electrons in the middle. They're going to share 2 electrons. So this hydrogen here had 1 originally. Now because they're sharing, now this hydrogen has 2. How about this hydrogen on the left? Now it has 2. When you share electrons to form a connection, that's called covalent. Covalent means sharing. When you share electrons to get to this noble gas configuration, in this case is 2. That's called a covalent bond. Sharing of electrons. When you share 2 electrons, that's a covalent bond. Share 2 electrons. And in this case, for covalent bonds, 2 electrons equals a bond. When you share 2, you can't share 3 electrons. You can share 2 electrons, you can share 4 electrons, 6 electrons, and we're going to talk about that pretty soon. So covalent bonds means sharing of electrons between 2 atoms. So, why do things form a bond? Right? Why do things form a bond? Do they talk to each other before they form a bond? What's connecting this forming a bond? So
The charges.
I'm kind of on the right track. There's some charges. The thing is, the Earth, the universe it's about energy, right? Conservation of energy. Like when you watch TV, you watch TV standing up or sitting down? Sitting down, because you want to be at low energy or you want to be at high energy? You want to be at low energy. So these atoms, same thing. They want to be at low energy. How could they be at low energy? So what happens is, this is energy here, the diagram, and then this axis here is the distance. So these two atoms here are really far apart from each other. They don't see each other. So we'll just say they're at this energy level here. They don't see each other. But when these two start coming close, if they happen to become close to each other, what happens? Their energy goes down. And at some point, at some distance, the energy is the lowest possible. But what happens if I squeeze these two atoms even closer together? Now they're going to want to repel, right? If you get too close to one another, what they're going to do, they're going to want to push each other away. So when they get too close to each other, the energy goes up, right? They don't like each other. They're trying to, the energy is going to go up because these two centers, the plus charges are too close to each other. Now they want to repel each other. So the energy goes up. But at some point over here, at this distance, we have low energy. And at this point, we have a bond. Right? Why do bonds happen? To lower its energy of the atoms. If you don't lower its energy, why the heck would these two combine? They won't combine, they just stay separate. But because when they combine, they lower its energy. Okay? So think about that like in real life. Suppose you have to pay every year, I'm making up a number, say $10,000 in tax every year. And then your boyfriend or girlfriend also has to pay $10,000 a year in tax. So you both are paying total $20,000. But how about if the government made a law says, oh, you get married, now instead of paying $10,000 in tax each person, now you only have to pay $7,000 a year in tax if you're married. So what are you two going to do? Get married, right? So now instead of paying $20,000 in tax for both of you, now you only have to pay $14,000 in tax. So you guys get married. How about if the government made a law says, okay, if you get married, you have to pay more in tax. So instead of you paying $10,000 a year in tax, now you have to pay $15,000 each. Are you two going to get married? No, because now it's just, you're going to pay too much. So you just won't get married. So atoms are the same way. Why would these two atoms marry each other, get connected? Because when they form a connection, they lower the energy. Energy gets lower. If they form a connection and the energy goes higher, they're going to get a divorce. They're always going to be fighting, right? So they're going to break apart. But if they could find a way to find the right partner, they can lower its energy. If they don't find the right partner, then they won't form a bond because the energy will go up high. So chemistry, this bond is, why do the bonds happen? We could talk about the technical things, but basically it means the energy is going to go lower if they form a bond. If the energy doesn't go, they're not going to connect, just be separate. So how can we lower the energy? By sharing electrons, getting these atoms to 8. These guys want to get the 8 valence electrons. And how can they get to the 8 valence electrons? Here's another example, chlorine. This valence electron, where is that valence electron located at? The s orbital or the p orbital? The p orbital. So here's the p orbital. One chlorine here. Oops. Yeah, one chlorine here, one chlorine over there. When they combine together, what is this? An orbital, right? What does an orbital mean? Where the electron is. So when these two orbitals combine, they could combine together. When they combine together, they could form a bigger lobe. And here, this is the atom, orbitals of the atom, but here's the orbital for the whole molecule. So when they come together, they could share these electrons. And then we draw the sharing of electrons like this. They're sharing these 2 electrons for chlorine. Right? Again, chlorine, if I just have chlorine by itself, am I talking about one chlorine atom Am I talking about Avogadro number of chlorine atoms,
Avogadro.
right? So this chlorine is never really by itself. And this chlorine goes, shoot, I just need one more electron to be like a noble gas. So what? It wants to take it, it needs one more. But this other chlorine here, its twin brother says, I need one more too. So what should we do? Let's form a partnership. Let's combine together and share these 2 electrons. So I could get 8 here and 8 on that guy. Right? So that's why I remember in the beginning of class, some elements do not exist by themselves. They exist as a molecule. So chlorine doesn't exist like this in nature. Why? Because chlorine, we're not talking about one chlorine atom, we're talking about many chlorine atoms. They're going to combine with each other just to make it more stable. When they combine to each other, they're going to form Cl2. Why don't they form Cl5? Why only 1 and 1 are combining together? Why is only 1 and 1? Because each chlorine only needs to share 1 electron. So they're going to form a connection here. So when you have 2 electrons, that's a bond. Instead of drawing it like this, we could also draw like this. Oh man, it's so hard to draw. Kind of hard to draw on this tablet. So whenever we're sharing 2 electrons, that's the same thing as this little bond there. Why isn't it Cl5 or Cl3 or Cl10? Because here I just need to share 1 electron from each one. And that corresponds to this compound here. So if you look at this, fluorine, bromine, all of these, they combine with each other. Why do they combine? Why doesn't oxygen exist by himself like an O? Why does it exist as like this? Right? Because we want to get to 8 electrons around each atom. How can we get to 8 electrons? By sharing electrons. So let's do an example here. Oxygen. How many valence electrons on oxygen? Anyone remember? If you don't remember, what are you supposed to do if you don't remember how many valence electrons oxygen has?
Was it 6?
How do you know it's 6?
Because
Column 6 on a periodic table, right? Exactly. No one memorizes how many valence electrons everything has. They just look at the periodic table and know how to read it. So oxygen has 6. So how could oxygen get to 8? I'm going to share these 2 electrons. Let's just say these 2 are going to share. Then this oxygen on the left has 1, 2, 3, 4, 5, 6, 7. I need 1 more to share. And this oxygen is going to come over here. Let's share these 2 over here. Now I have 8 on the left, 8 on the right. So let's clean this thing up. This is kind of messy, right? So I'm going to say, okay, I got an oxygen, and these sharing 4 electrons. Sharing 1 electron is a line, a bond. Sharing 2 electrons is another line here. How many electrons do I have outside? Got 1, 2, 3, 4. 1, 2, 3, 4. So this is the Lewis structure for oxygen. So oxygen doesn't exist by itself because there's always another oxygen atom next to it. And it'll form O2. So oxygen in nature exists as O2. Now I have oxygen plus I have like a hydrogen. Now the oxygen doesn't have to combine with another oxygen. It could combine with something else. But oxygen doesn't exist by itself, one atom. It exists always as, in nature, if I only have oxygen, it exists as O2. And why is that? How can we explain that? Oxygen wants to have 8 valence electrons. How could I get to 8 valence electrons? By sharing. And when I share electrons, I form, in this case, like look at iodine, those 1 line is a single bond. What do you think 2 lines mean? Double bond. What do you think 3 lines mean? Triple bond. Which one you think is stronger? A single bond, a double bond, or a triple bond? Which one you think is stronger? A single bond, a double bond, or a triple bond? Triple bond, right? It's like if you have a car and you're trying to tow another car, are you going to use 1 rope, 2 ropes, or 3 ropes? Which one you think have a better chance when you have your car and you try to tow another car? A single rope, a double rope, or triple rope?
Triple.
Why? Stronger. Right? So little things like this, we go, oh, we have different bonds and maybe there's different strength. Right? It's a little thing to think about. And why is this thing happening? How do we explain all this stuff? We call it the octet rule. Things want to get to 8. Is this octet law or is it octet rule?
Rule.
Rule, right? What are rules meant? Rules are meant to be what?
They say followed.
Broken.
Oh, broken?
Okay.
Oh, see how good I am.
You're on the right track. We know who's the good, the good citizen, and then the not so good citizen, right?
Oh, see?
I'm just joking. I'm just joking.
Extra credit. No.
On the
Yeah, so
internet.
right. So rules are meant to be broken. So there's always exceptions to that rule. So helium can't have 8. It's too small. Things on column 1, column 2, column 3, there's not enough electrons, so they can't get to 8. So there's always some exceptions to that rule.
So they're the one that gives away electrons, right, to the other element.
Sometimes they could give away, but sometimes they can't reach it. Suppose like boron. If I lose electrons, the boron is going to become like helium. It's 2 electrons. I can never get 8 electrons around boron. It's just too small. So basically, atoms that are too small can't get 8. Can't get to 8. And there's more exceptions to this rule too. So this just gives you an idea. This octet rule is just a simple model. There's a lot of exceptions to the octet rule, but this will give us a good idea how bonding works. So how do we get to 8? Sometimes we have to share 2 electrons. When we share 2 electrons, 1 line, single bond. Sometimes we have to share 4 electrons, double bond. Sometimes we have to share 6, triple bond. Right? And when we see these double and triple bonds, typically with these type of atoms, right? Just from doing experiments, we see them from certain type of atoms. All right. So there's going to be some atoms. So these in the center, they're being shared. How about the other atoms on oxygen? I mean, there's other electrons on oxygen. Those, they're not being shared. Only some electrons are being shared, some are not. The ones that are being shared, they call that bonding. Bonding electrons or bonding pairs. Why do we call them pairs? Because we need 2 electrons to form a bond. Then the ones that are not being shared, we call them lone pairs. They're kind of like loners. They're by themselves. They're not being shared. Bonding pair, they're being shared. And because of loners, they're not involved in bonding. Sometimes they're called bonding pair, non-bonding. Right? Also non-bonding pairs. So you see here, non-bonding electrons, bonding electrons, lone pair. So those are terminology you should be familiar with. So let's look at this example of water, what someone mentioned before. How many valence electrons are on oxygen? 6. Hydrogen, 1. How much does oxygen need? Oxygen needs 2 more electrons. So let's share with this hydrogen over here. Now this oxygen only has 7. Well, we're not talking about one hydrogen atom. Maybe there's another hydrogen atom floating around. Then these two are going to come together. Now oxygen is full. Oxygen has 8. Can oxygen take more than 8? No. There's a, we're going to just say no because it's full. It's like a noble gas configuration. So this octet rule helps us predict that H2O is 1 oxygen and 2 hydrogens. H2O is not, water is not, it doesn't form H4O or H4O5. No. How could hydrogen and oxygen come together to get 8 electrons around oxygen? H2O. So this octet rule predicts why water is H2O, not H4O, H10O. Because this formula for water, this is the, kind of think about this as the answer in the back of your book. This is what nature tells us, what water is, H2O. But how can we predict it? Why is it H2O? We come up with the model, this octet rule, sharing of electrons. Why would they share? They want to get to 8. Oxygen wants to get to 8. So that helps us predict or explain why water is H2O instead of H5O. I think we did this one earlier. Oxygen has 6 valence electrons each. How could they get to 8? By sharing valence electrons. And when what we predict, there's a double bond. Huh. How can we determine, then we'll do the same thing for nitrogen. Nitrogen has how many valence electrons? 5. How can nitrogen get to 8? Maybe they're going to share here. Now I have 6 valence electrons on one side. Maybe I got to share over here. Now I got 1, 2, 3, 4, 5, 6, 7 on each nitrogen. Oh, I need one more. Maybe this one over here is going to share with this one over here. Now I have 8 and 8. So now let's clean this up. This is so messy, right? So what that's going to look like is going to look like this. Sharing 6 electrons. But 2 electrons is a bond, so it's a lot nicer, cleaner to draw it this way. 2 electrons are not involved in bonding, and these electrons in the middle are involved in bonding. So we have a total of 8 valence electrons on each side. Here we have 6, here we have 2, so that's a total of, and here we have 2. So if you just look at this, we have 8. For this atom here, we have 8. And that predicts nitrogen is a triple bond.
So the 3 lines are to take it as those 3 dots that connected.
Those 3 dots here are these 3 lines here.
Which are the 6 dots that you connected that make the 3 lines.
Yes.
Okay.
We like to draw it this way. It's a lot simpler. This way is kind of like, yeah, we got 6 dots. That's nice. But we like to draw lines showing that there's actual connection. So these are called molecules. So can I have more than one molecule? Yeah, I could have N2 over here, another N2 over here, another N2 over here. So in here, there's what's going on here? You got a triple bond, covalent bonding. So these are all individual molecules. Here's a little picture. You got one molecule here. Whoops. There's a lot of covalent bonding going on, but these molecules could kind of interact with other molecules. And we're going to talk about that later in maybe chapter 10 or chapter 11 later on. But so there's covalent bonds are the bonds within one molecule. but other molecules could interact with other molecules, and those are called intermolecular attraction. So these are not bonds. These are just some like an attraction. But what we're focusing on is the actual bonds that happen inside a molecule. So what do we say about covalent bonding? What does covalent bond mean? Anyone want to chime in?
Bonds that share electrons.
You share electrons. But a lot of you might have a brother or sister, but you don't have a twin brother and sister. So if you don't have a twin, that means one of you is stronger than the other one, because one's older. So when you share, do you have to share equally, or you can share unequally? You could have unequal sharing, right? So in this situation, this is an H plus. It has no valence electrons. This one has these two valence electrons here. And what could happen, they could still share these two electrons, but those one electron doesn't have to come from this one electron doesn't have to come from this one. Covalent bonds mean sharing two electrons. Doesn't matter where those two electrons come from. So here, you could have sharing, but these two electrons came from here. So that's called coordinate covalent bonding. When both electrons are donated from one atom. So one atom is contributing these two electrons. Maybe you're the older sibling, your younger sibling doesn't have a toy. So what you have to do, I'm just gonna share both of these. We're gonna share these two, and we're gonna make a connection. So you guys can be good brothers and sisters. So this one has no toy, this one has two toys. This one's gonna share both of them. So the sharing doesn't have to be equal, 1-to-1. They can come from only one. That's called a coordinate covalent bond. Now, getting back to our other situation, maybe this is one atom, this is another atom. Remember chlorine? How many electrons does chlorine want to get? How many electrons does chlorine need to be a noble gas? It needs one more. So it really wants that electron. But it's not strong enough to take it away from hydrogen. It's not strong enough to take it completely away. But it's kind of strong enough to kind of like pull it more towards its side. So think about this one as the big brother, big one. This is the small one. One's going to be stronger than the other. So they can still share, but the sharing is not going to be equal. The sharing is going to be more towards that end, the chlorine. The electron is going to be more on the chlorine side. So see this little bubble, little shape? What does that shape mean? Anyone remember? What does that shape, like if it's an s orbital or p orbital, what does the shape mean?
Remind us, please.
What does an s orbital mean? Why does the s orbital have a certain shape?
Oh, it's what axis it's on. Well, like when it's on X, Y.
Why do these orbitals have a shape? What's the shape trying to tell us? What is the shape telling us?
Does it have to do with what's inside and what's outside together, all bounded together?
What's inside the shape?
Electrons.
The nucleus with
Electrons. Probability of what?
Of where they are.
Where they are. Why is the probability bigger on this side than the other side? Because one
More.
atom is pulling the electron more on its side. So that's why the probability is bigger on one side. If the probability is bigger on one side, that means the electron is going to be on one side more times than the other side. So that must mean this side is going to be a negative charge. But it's not a complete negative because it didn't completely take away the electron. So we call this a partial negative. And this on the other side is going to be a partial positive. So we call that electronegativity. Some atoms want electrons more than the other atom. If it wants it more, the electron's gonna probably be on that atom more than the other atom. And when the electron's more on one side than the other side, we're gonna have a slight charge difference. Partial negative on one side, partial negative, partial positive on the other side. Okay? And that terminology is called electronegativity. So which atoms all atoms have slightly different electronegativities. Some, these guys in the corner have high electronegativity. They really want the electron. These guys over here, they really don't want the electron, or they don't care about it. Why do these guys on the right here want it? Because they're so close to become like a noble gas. They really want that one electron. The ones on the left, they don't really want it, but they'll keep it, or they could lose it. So these guys really want it. These guys don't really care. So some guy came up with a little quantitative system, give it a number scale. Fluorine is the most electronegative. 4.0 is the highest on the scale. And then they have a different scale. So someone just made up the scale. This guy named Linus Pauling. And again, California. This guy is from California, figured this out. So some atoms are more electronegative than other atoms. So it gives it like a little numbering system. 4, 3.0, 3.5. So what happens is,
No hydrogen.
what was that?
There's no hydrogen.
Hydrogen they put over here. (2.1). So how are we going to use this data? So what type of bonds are there? We talked about there's something called covalent, ionic. Then there's something in the middle, polar covalent. That means there's sharing of electrons, but the sharing is not equal. That means this one's going to have a charge, or partial charge. Partial positive or partial negative, right? So the covalent bond means sharing, but then it's going to have a difference in charge. So bonding, how we determine bonding is by differences in electronegativities. What the heck does that mean? So what we're going to do, I'll give you this little example. So when we have an ionic bond, one atom completely removes an electron, the other atom completely lost it. So what happens? We have a plus charge and minus charge. So there's no sharing of electrons. There's just a plus and minus charge coming together. Covalent, equal sharing, that means this little shape means the probability of finding an electron. Probability of finding the electrons are equal on both sides, so there's equal sharing. Polar covalent, there's sharing of electrons, but the sharing's not equal. More electrons are going to be on the left side than the right side. So when you have equal sharing, that's a covalent. When you have completely removing an electron, creates a charge that's ionic. And we have sharing, but then that results in the partial positive, partial negative, that's called polar covalent. So the covalent is one extreme, ionic is another extreme, and polar covalent is sort of in the middle. So how are we going to figure out which compounds are polar, which ones are non-polar, which ones are polar covalent, and all that? So what we're going to do is look at these two atoms. And those two atoms, we look at this table over here, carbon and sulfur. Carbon is 2.5. Sulfur is 2.5. What are we going to do with that? We're going to get those two numbers, subtract the two numbers, and we get a 0. And what are we going to do with that 0? We're going to go back to this table here. If the difference is between 0 and 0.4, that's a covalent bond. If we subtract the two numbers and it's between 0.4 and 2, then we call that a polar covalent bond. If we subtract the two numbers and the number is bigger than 2, then it's ionic. So this gives us like a guide on how to tell us that quantitatively, instead of just guessing, is quantitatively, is it a covalent, polar covalent, or ionic? Looking at the two numbers, we subtract the two numbers, and what do we get? In this range, and this range, it's going to tell us it's polar covalent, or ionic. So nitrogen and chlorine, subtract the two numbers, 0, that's a covalent. Phosphorus and oxygen, those two atoms, if they form a bond, is going to be 3.5 minus 2.1, 1.4. Ah, that's a polar covalent. And another way to show this polar covalent bond is sometimes you might see something like this in your textbook. What does that mean? That means that this phosphorus and this oxygen, they form a bond, a polar covalent bond. What does that mean is, so now there's a positive end and a negative end. So which is the negative end and which is the positive end? So one way to draw it is we draw a P, we put a plus sign there, and we put an arrow. Where's the arrow pointing to is where the electrons are going. So electrons are going to be on this side. And you put a little plus sign there. What does that plus sign mean? That's the plus side, and the other side is the negative side. So this is the plus side. Where's the arrow pointing towards? Where the electrons are going? The negative side. Nitrogen and carbon, 3.0 minus 2.5 is 0.5. Okay, it's bigger than 0.4, so that is covalent. So what do? Carbon, where's the electrons going to be? You look at whichever one's a bigger number, 3. So that's going to be this one for nitrogen. That's going to be the negative end. This is going to be positive. So it's not a real negative, it's like a partial negative. So we draw this little thing like this. Delta sign. So we want to be quantitative. So they're both polar. So which one's more polar? And which one has more of a charge? So there's something called dipole moment. So we're not going to go in that calculation, but there's a way to calculate this dipole moment. So basically, if it has a dipole moment, that must mean it's polar covalent. And we have something that's polar covalent, that means you have a charge on one side and a charge on another side. We have charge on one side and another side, that's called a polar. Something's polar. Just like the Earth, we have a North Pole and South Pole. They are opposites. So a polar compound is opposite ends. Opposite end here is a plus charge and a minus charge. So that's why we call it polar covalent. Opposite ends, plus and minus, and they're sharing electrons. Everyone good?
Agreed.
And look at this CO. If I just look at this thing by itself, that would be polar. Just look at one half of the molecule. If I have the C and O, yes, that's a polar compound. Oxygen is more polar, so the electrons are going. This is going to be a minus end. This will be the plus end. But the whole molecule looks like this. CO2. Is this compound polar or non-polar? What do you guys think? Polar or non-polar? Is there more electrons on one side or the other side? Or no? So what's happening here is, think about like a tug of war. Suppose this is you on this end. You're pulling this way, and you have your twin brother pulling this way. Oxygen pulling that way. Could oxygen have more electrons on this side than that side? If you were both pulling in the same opposite directions? No, you're identical twin brothers. I cannot have more electrons on one side than the other side. So this compound, even though this is non-polar because of the shape. But I just have C and O, yes, that will be polar. I'll have a minus N here, a plus N here. But since this is not, this is linear, and I got oxygen on one end, oxygen on the other end, they're pulling the same strength back and forth. So I can't have a positive N, I can't have a negative N. So this will be non-polar. So the shape of the compound could also impact the polarity. Even though the individual atoms, they're going to be polar, but that because of the shape is going to be non-polar. How can we test this? We could just get the CO2, put it through a certain machine we have, and then we could check if there's a positive or negative N on this molecule. Look at this one. Another example will be NH3. What do you think NH3 is going to be, polar or non-polar? If you draw NH3 like this, that would be non-polar. If you draw NH3 like this, that would be polar. This would be non-polar. So we have a machine. We could put this thing through like a little electrical chamber, and then we could see if this thing has a charge. So we have an equipment to tell if a compound has a charge, or if something's polar or non-polar. So they do this experiment, and they go, what do you think NH3 is, polar or non-polar? What do you guys think? NH3, polar or non-polar?
Non-polar?
Okay, somebody says polar. Somebody says, anyone else? So now we put it through this machine, and then we figured out, oh shoot, NH3 is polar. It has a minus side and a plus side. Then what does that tell us? NH3 cannot be this shape. NH3 has to be a shape like this. So this idea of polarity, non-polar, it kind of tells us, oh, it can't be this shape here on the right. It has to be a shape not to be polar. So little things like this tells us that indication that NH3 is, the shape is going to probably be like that. It's going to be like this on the left. So how do we do Lewis structures? We got to do, this is going to tell you, like your book's going to tell you how to do it. What we did is we want to look at valence electrons, right? Thing wants to get to 8 electrons, but there's some things that can't get to 8, like boron, hydrogen, they're too small. But things want to get to 8 valence electrons, octet rule, right? Sharing of electrons, we can share 2 electrons, 4 electrons, 6 electrons to get to 8, octet rule. So we'll do a little exercise here. Let me see how many more slides we got left today. We got a long way to go.
Is our following exam, I think it said 7 and 8. Is that,
Next exam?
yeah, is that accurate? Chapter 7 and 8?
Well, I can't tell from here. Again, I'm not good at memorizing stuff, so I have to look at my syllabus.
Yeah, my memory is, I don't know.
Yeah, so you just have to go over here. If you want to know what's going to be on exam, you go, okay, exam 3, 7, and 8. Yes.
Okay. Thank you.
All right. Out of this. All right, so this one, how are we going to draw the Lewis structure for this one here? SCO2. Usually when we write the these, if there's more than 2 atoms, the central atom will usually be the front one, but that's not necessarily true. So what we're going to have to do is sulfur. How many valence electrons are on sulfur? 6. Chlorine? 7. Well, I got 2 chlorines. I don't know which, so I just got to figure out how could these 3 be connected so I could get 8 valence electrons on each one. Let's just share here. Oh, chlorine has 8 now, it's happy. Sulfur has 7. Okay. This one has 7. What can I do? Let's have these 2 share. Now I have 8 there, and I have 8 there. Is everyone happy? Yes. So, what's the valence? Then I'm going to clean this up. When I clean that up, it's going to look like that. This is going to be the Lewis structure for that guy there. I could also draw this one a different way. So this is the very common way to after you clean everything up. This is what's going to look like. And by doing this Lewis structure, I figured out that the sulfur is in the middle. CO2. Oops. Delete all that. I already drew this out here. So the next one, CO2. Draw like that. I think you can work this out on your own, the CO2 one. Now there's some compounds that contain both covalent bond and ionic bond. So inside here, inside this bracket, we have a single bond, double bond. That is a covalent bond. So we have covalent bond going on in here. Then this plus charge and this minus charge, we have a ionic bond. So in this compound, we have both covalent bond and ionic bonding happening. So I think this is a good place to stop. So stop recording.